Ever wondered how AI models like GPT or BERT achieve such human-like understanding? The answer lies in a revolutionary architecture that's redefining machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, exploring their attention mechanisms, scaling challenges, and the cutting-edge research pushing their limits. If you're a developer, researcher, or just curious about AI's next frontier, this is the breakdown you've been waiting for. Before transformers, sequence modeling relied on RNNs and LSTMs, models that struggled with long-range dependencies and parallelization. Then came the 2017 paper Attention is All You Need, introducing a radical idea, replacing recurrence with self-attention. This allowed models to weigh relationships between all tokens in a sequence simultaneously, enabling parallel computation and capturing long-range patterns. But how does this attention mechanism actually work? Let's break it down. For every token in a sequence, the model generates three vectors: queries, keys, and values. The attention score between two tokens is calculated by taking the dot product of their query and key vectors, scaling it by the square root of the key dimension, and applying a softmax to normalize. This score determines how much each value vector contributes to the final output. Mathematically, it's attention QKV equals softmax, QKT slash square root DKV. But this is just the foundation. Modern transformers expand this with multi-head attention, allowing the model to focus on different aspects of the input simultaneously, like a team of specialized processors working in parallel. As models grow, so do computational costs. A 100 billion parameter transformer requires massive resources, but researchers are tackling this with innovations like sparse attention, where each token only attends to a subset of others, and efficient architectures like Longformer or BigBird. Then there's the problem of training data. How do you scale without overfitting? Techniques like parameter sharing, knowledge distillation, and dynamic computation graphs are reshaping how we train these systems. Recent breakthroughs include mixture of experts, MOE, layers, which route inputs to specialized subnetworks, drastically reducing compute. Then there's the rise of vision transformers, ViTs, which apply self-attention to images, challenging CNNs as the dominant architecture. And let's not forget the quest for efficiency. Models like mobile ViT and TinyML transformers are making these systems viable on edge devices. But what about the theoretical limits? Researchers are now exploring how to make transformers more interpretable, robust to adversarial attacks, and capable of few-shot learning. Transformers aren't just a trend, they're the backbone of modern AI. From their elegant attention mechanisms to the relentless pursuit of efficiency, they're pushing the boundaries of what machines can understand. Whether you're building the next big model or just curious about the tech behind your favorite AI tools, the journey of transformers is far from over. Stay tuned, keep experimenting, and remember, the future of AI is being written in the attention matrices of these remarkable architectures. If you want to explore the code behind these concepts or dive deeper into specific architectures, check the description for links to papers, tutorials, and open-source projects. Like this video, subscribe for more deep dives into AI's most complex ideas, and let me know in the comments, what AI topic should we tackle next? Thanks for watching. Keep learning, keep building, and remember, the most powerful models are the ones we continue to refine.